everyone, and welcome to today's webinar, Modicon M580 OPC UA Communication Module. Thank you for joining, and we are about to start. But before, we would like to cover a few housekeeping items. We'll be running a live Q&A at the end of the presentation. So if you have any questions during the webinar, you can click on the Q&A panel at the right bottom or enable this feature on the three-dot icon on the slide area. And you submit your question. We will return these during the webinar. But if a fuller answer is needed or we run out of time, it will be answered later via email. We do capture all questions. And now I would like to pass it off to our very first presenter. Lou, you can go ahead and begin. I'm going to give you the availability to do that.
Awesome, Sheena. Thank you very much. Thank you very much. And let me go ahead and share my screen. Okay, you should see my screen. Is that right, Sheena? Okay, cool. So thanks everybody for joining the next version of the Modicon User Group. Today we're going to talk about OPC UA and how to set up PLC cyber secure communications. And it's always a surprise to me is that, you know, for years now, we've had cybersecurity built into our PLCs, lots of different features around it. This is one of them, and many people don't set this up. And I'm baffled as to why, because it's so easy to do that. Joining me today, we have Bobby Singh and David England. They are our systems architect experts, our SAEs here in the U.S. They're going to talk about setting up the OPC UA cyber secure communications, and they're part of my team across the U.S. We have about 13 people. Also joining us is Robert Willis, and he's going to give us, for those who are using our stuff today, he's going to give us a little tip and trick. It's a little 5-minute overview of some really cool features actually around firmware built into our stuff. And so you're going to want to see that, and that's going to happen first. But before we get there, just for clarification, I grabbed this slide from the OPC Foundation. And it basically goes over, all the uses of OPC and what they're working on. As you can see, there are lots of things, uses for OPC. Typically, OPC communications has been between SCADA and PLC. Today, we're going to talk about SCADA and PLC encrypting that. We're also going to talk about PLC to PLC using OPC UA, which is kind of something new. We normally, you don't associate OPC UA with controller to controller. But OPC is also working on something they call field exchange, and you've probably heard about it, but they're also working on other things like wireless, on safety, motion. And so there's a full portfolio of this OPC UA protocol that's going on, remote communications, MQTT. All of that. And so today we're going to isolate our conversations around PLC to SCADA and then controller to controller. Certainly in the future, Schneider Electric is embracing the entire OPC UA communication stack. So you'll hear more about that in the future. Just a reminder, right? We try and keep to these things. Today is going to be all around PLCs, SCADA, HMI, cybersecurity. That's what we're going to focus today on this user list. As a reminder, and I will put the link into the chat, although you can search it, we have a Modicon User Group on YouTube, and this is our playlist. Our team puts together videos to help you, create or help you integrate our stuff easier, to make our stuff easier to use. Our latest one is if you're using the M580 and you want to use TM3 IO, the smaller IO through a bus coupler. We have a video, a short 11-minute video that kind of goes through how to set that up. Please connect with me via LinkedIn. The invitations for these, although you may have received this through an email invite, we also have these through LinkedIn. Notes for today's webinar: please direct your questions to the Q&A. And, it kind of keeps all the questions together as opposed to the chat. If you want to know more, please contact me. If you want to know more about what we're doing or you want to know how to use this, please send me an email and we'll have somebody give you a call to kind of walk you through your particular application. There's my email address. And then at the end, we have a little short survey. If you can fill that out, I appreciate it. It helps us get better. We want to make sure that we're hitting the mark here today. So with that, I'm going to pass it along to Robert Willis, who's going to talk about firmware. Robert, it's all yours.
No, thank you, Lou. All right, I'm sharing my screen so you should see it. And what we're going to talk about today is something that we get lots of calls on all the time, and that is, how do you find the most current firmware that Schneider Electric has for their Modicon product line? So specifically, we're going to talk about EcoStruxure Automation Device Maintenance version 3.2.124.0, and I will drop the link to download this software from Schneider Electric in the Q&A. But what I want to point out is some new features that we added to it. And when you launch EcoStruxure Automation Device Maintenance, you're going to see this icon at the toolbar up top say Settings, and you're going to see the cloud with the green checkbox. If you're connected to the internet, what the system is doing at this point in time, it is downloading a list of firmware that you might have available on the system. And over here under the tab called Data Package, here is a list of all of the firmware that it found on our server, on our protected server. And if I click on one of the expanded, you will see that I can get the firmware for the analog high-level input module, and it's the 1.4 and 1.3 firmware. The icon right here indicates that it's available in the local repository, meaning I have already downloaded it. If I come down here and show you one of the systems where I have not downloaded it, this is the firmware. It's up in the cloud repository. And if I click this button right here, it will download the firmware to your personal computer. The next step would be you're going to go out and locate your PLC on the network. So if I go to Settings, we are going to use two different protocols to search your network. DPWS stands for Device Protocol Profile for Web Services, and then Modbus TCP/IP. What we're going to do is we're going to use Modbus TCP/IP opcode 43, and you can control how many devices I look for. So on my network here, I'm picking the communication adapter, and we're going to issue a DPWS request on Modbus TCP/IP. In order to make it go real smooth today or fast, I'm going to search my PLC USB connection at this address range. And once that is done, I click the green button, I hit Start. And of course, as you can see, it rapidly found my Modicon M340 out here on the network. And it currently tells me the current firmware that's in the controller. If I log into the controller, and that default password is FW download. If this was a Modicon M580 and you have changed the password, you would need to know what that is. I hit Save and Connect, and it tells me the current status. I can come over here and select Update, select Firmware, and it will tell me that firmware 3.51 IR7, which happens to be the same one I have in my CPU, if I wanted to, I would download it from the cloud and hit the Save button, and it would automatically, with some extra prompting, would automatically download the firmware to your M340. Now, once you download all the firmware to your computer, you can then go to the folder where I store it, and here is where it's stored on your computer. You can take all of the data that's in that folder and copy it to another computer, let's say one that's not on the network, if you will, and it would automatically show you that data. So here's all of the files that I have in that folder. And I could copy all of those firmware files to another computer that may not be on the network, and you could do the download then. That was a quick tips and trick for the EcoStruxure Automation Device Maintenance software. Look forward to helping you in the future. And I'm now going to turn it over to Bobby. Bear with me. There you go, Bobby.
All right. Thank you, Robert. So up here. All right. Good morning and good afternoon, everyone. Thanks for taking the time to join us today. In today's Modicon User Group session, our goal is to show you how easily you can secure and encrypt communications between Modicon M580 and any other connected networks using BME NUA 0100 communication module. We also refer to this module as NUA in short, and you'll hear us throughout this presentation use that term. NUA module is a very advanced communication module that acts as a firewall between Modicon M580 and any other connected networks. Let's take a look at today's agenda before we move on. First, I will go over the current connectivity to Modicon M580, which is important as it will help you understand why you might want to add the NUA module to your architecture. And before we move on further to the module, Dave will go over what OPC UA communication protocol is and some of the great benefits of it. Followed by introduction to the NUA module, in which I'll cover some of the physical characteristics and the main key features that allow you to secure and encrypt your data from the M580. Then we will review some architecture use cases, followed by a live demonstration, in which I show you how easily you can enable some of the key features in OPC UA, the NUA module. All right, let's go over some basic information on how M580 controller communicates and exchanges data over the backplane. It's important for us to understand the difference between the X bus and Ethernet bus, since we will talk about it throughout this presentation. If we take a look at this empty 4-slot Ethernet backplane, you can see all 4 slots have 2 connectors. You have Ethernet connector on the left side for Ethernet bus and an X bus connector on the right side for X bus. M580 uses both Ethernet bus and X bus for communications to obtain and exchange data between many X80 I/O modules and communication modules that are installed in each slot. M580 mainly exchanges data with all NOC modules over the X bus. And it's doing that so at the rated speed for X bus, and that is 12 megabytes per second. On the other hand, M580 exchanges data between CPU or M580 itself and the NUA module over the Ethernet bus, and it's doing that so at 100 megabytes per second. Keep in mind that Ethernet backplane port is disabled on all NOC modules by default, but can be enabled through the software. There are certain risks associated with enabling the Ethernet backplane port on the module, which I will explain later on, a few slides from now. But the Ethernet backplane port on the NOC module is mainly used to pass through for device access, but all the data such as Modbus TCP is exchanged over the X bus. Main purpose of this slide was to make sure we understand how M580 communicates to NOC and NUA modules over different communication buses. Let's move on to the current connectivity to Modicon M580. Let's understand the capabilities of most commonly used communication modules for M580 architectures today. We have NOP 301, 311, and 321. All 3 modules support Modbus TCP and Ethernet IP, as well as I/O scanner capability. Some of the key differences between three of these modules is NOP 301 and 311 are very similar, except that 311 comes with factory cast and program viewer, which allows you to view your control expert logic over a web page for troubleshooting purposes. NOP 321, on the other hand, acts as a router with IP forwarding capability. The IP forwarding feature in a device, essentially what IP forwarding is, it's a feature in a device that helps us send data packets to the right place, like a traffic cop directing cars. It makes sure the data gets from your device to its destination on a network, ensuring smooth communication and information sharing. I will demonstrate how easily you can configure IP forwarding on the NUA module in use case 2. Because one thing to note, on NOC 321, IP forwarding have to be enabled and configured manually. Versus on the NUA module, you do not have to worry about that. Now let's go over some of the limitations when it comes to the modules that are currently used. So the traditional way of connecting controllers such as M580 to upper layer system, and upper layer system could be any SCADA application or any other software application that needs to communicate with M580 and get data out of it or write data to it. We see NOC 301 that's commonly used for connecting SCADA networks to the controller, or M580 in this case. The Ethernet backplane port is disabled on the NOC 301 by default, but it can be enabled in the software. We do not recommend enabling the Ethernet port since it creates security risk. If you enable the Ethernet backplane port on NOC 301, now M580 private networks such as remote I/O and distributed I/O is completely exposed to any connected network such as SCADA network. Now anybody that's connected to these network, any device, could completely see what's connected on the M580. It's no longer isolated. Also, enabling backplane port allows M580 DHCP server go through the Ethernet backplane bus out the backplane port of the NOC module and issue DHCP requests to any connected devices, and that could create a network issue. Now let's move on to some of the limitation on the NOC 301 module. Both NOC 301 and 321 uses XBus to exchange Modbus TCP data. On the other hand, the NUA module uses the Ethernet bus, giving you higher performance when you're moving Modbus TCP data. NOC 301 also does not have IP forwarding capability. It's a basic simple 3-port switch. Lastly, both NOC 301 and 321 has IPsec feature, which stands for Internet Protocol Security. It's available on all NOC modules, but it's not too user-friendly to configure. It requires manual configuration on both on the module and the Windows firewall. And you may wonder what IPsec or Internet Protocol Security is. IPsec allows you to create a secure tunnel between your engineering workstation and the module, very similar to VPN. And it allows you to authenticate and encrypt your data that's being exchanged between M580 and your engineering workstation. I will demonstrate later on how easily you can set this up on the NUA module. You also see some M580 architectures with NOC 321 since it has the IP forwarding capability. IP forwarding on the NOC 321 allows you to access field devices on both remote I/O or isolated distributed I/O networks. But there are some limitations to that. Even though it has IP forwarding and the IPsec feature available, you cannot use both at the same time. So if you want to take advantage of IP forwarding, you cannot enable cybersecurity, and vice versa. Also, both modules have limited firewall features. Essentially what I mean by that is that you cannot control what goes in and out of the modules. On the NUA, you have complete control over that. You can set firewall rules. Once again, the purpose of this slide was to make you aware of some of the limitations that we currently see with the NOC modules. But I'm not telling you to remove these from your architectures because you still need NOC module to be able to do I/O scanning for your field devices. But simply, if you have any upper layer system that you need to connect to, such as SCADA applications, then consider adding a NUA module that helps you get rid of these limitations. I'm going to move on to what OPC UA protocol is and some of the great benefits of it. So I'm going to hand it over to Dave.
Okay, thank you very much, Bobby. So first, we're going to look at what the history of the OPC protocol is. So the OPC standard was first released.
Bobby still has the sharing screen, so I don't know if you're sharing something as you're talking, but
Yeah, Sheena, I'm gonna drive the PowerPoint right now because I'm gonna take over again. So it's just 2 slides.
awesome.
Okay, so the OPC protocol was created in 1996 with the purpose to abstract PLC-specific protocols such as Modbus or Profibus into a standard protocol for HMI and SCADA systems to interface with. What this did was it allowed software vendors to develop products based on a single standardized protocol rather than needing to support multiple vendor-specific drivers. OPC was founded by and is managed by the OPC Foundation. Initially, the OPC standard was restricted to the Windows operating system. The acronym OPC was born from OLE, which is Object Linking and Embedding, for process control. These specifications, which are now known as OPC Classic, have enjoyed widespread adoption across most industries. As useful as OPC Classic is, it also has many limitations. It is not bandwidth efficient. It has limited data modeling capabilities. It depends on Microsoft DCOM, and DCOM is prone to many security vulnerabilities. It is difficult to troubleshoot, and it doesn't have much in the way of native cybersecurity. There is no authentication or encryption between servers and clients. So to mitigate some of these limitations, OPC UA was created in 2008. And as such, OPC now stands for Open Communication Platform and UA for Unified Architecture. So what is OPC UA? OPC UA is a modern, secure, open, and reliable platform for industrial communications. OPC UA is platform independent, which means it works on different types of systems, including Windows, Linux, and embedded devices such as PLCs or HMIs. This enables OPC UA to be a single communication protocol across a wide range of platforms. OPC UA has built-in cybersecurity utilizing encryption and authentication. OPC UA uses standard transport protocols such as TCP/IP and HTTPS, making it IT and network friendly. This also makes it easy to troubleshoot with standard tools such as Wireshark. OPC UA also provides an object-oriented address space, including variables, methods, and events. Consider the OPC UA diagram on the right. We can think of this object model as a digital blueprint of a factory. Objects represent real things. We have variables for holding information, like the value of an analog input. There are methods that can generate actions, like moving a robot to a specific XYZ coordinate. There are events for notifications. This would most commonly be an alarm. And we also have metadata for data contextualization. This would be something like a timestamp or engineering units. So why do we need OPC UA? We have field bus protocols like Modbus TCP, which are great for moving data. There are a couple problems with these traditional field bus protocols. They're not natively secure, and they don't provide a rich meta model and a rich service architecture like OPC UA. OPC UA allows us to leverage a natively cybersecure, rich, object-oriented data model as a single standard from our OT devices to our IT servers, so we can simplify engineering in a scalable architecture. Now that we've discussed the UA protocol, I'm going to give it back to Bobby, who's going to discuss the OPC UA solutions we have from Modicon.
Thank you, Dave. Now that you understand what OPC UA communication protocol is and some of the benefits of it, let's go over a current OPC UA offer from Schneider Electric. With Schneider OPC UA solutions, you are able to have flexibility with your architecture. We have software solution, and it's called EcoStruxure OPC UA Server Expert that lets you run the OPC UA server on a Windows machine. And then we also have in-rack hardware solution that allows you to have the OPC UA server right next to M580. And also recently we introduced new OPC UA client capability for M580 via function blocks that Dave will demonstrate later on in our presentation today. Let's go over the two differences, or the key differences between these two software and a hardware solution. So the software, OPC UA Server Expert, needs to be hosted and installed on Windows Server. It could be at the top layer here. It could be next to your SCADA applications, or it could be on the same server. And it could support multiple clients, right? As soon as you meet the hardware limit or the client limit on the module, you need more than 20 clients or 10 clients, then you can add software solution to your architecture. It could also support multiple controllers, right? You can have multiple controllers all under one OPC UA server. You can even add legacy platforms such as Modicon Quantum under the OPC UA server expert. Both software and the hardware support Modbus TCP devices. Software itself is very scalable. The hardware on the other side, the BME NUA 0100 module, it's in-rack solution. It sits right next to the M580, has to be on the main backplane, cannot be placed in the remote I/O. You could have up to 2 NUA modules per M580 system. And each module can have 10 OPC UA clients connected at a time. If you need more than 10, you will need 2 modules. The hardware solution simplifies integration with SCADA applications since there is no need to install any additional software nor needing a license. You can easily manage it with a built-in web server. Also, when using the hardware-based OPC solution, now you have secure and encrypted communications directly into your PLC. Let's move on to the NUA 0100 module. First, let's go over the front view of the module. You have a typical LED display that provides status of the module and is great for troubleshooting. You also have a front Ethernet port, a 1 gig Ethernet port that allows you to transfer data at speeds of 1 gig or 1,000 megabytes per second. It's the exclusive port if you want to access the OPC UA server, but also is the main port if you want to access M580 also. Now let's take a look at the back view. You have on the left side here, you have the XBus backplane port, and on the right side, you have Ethernet backplane port. The XBus is mainly used for 24 DC power and rack addressing only. There is no other communication is performed on the XBus or NUA module. The Ethernet backplane is used to exchange all data between M580 and the NUA module. There's also a rotary cybersecurity selector switch, or what essentially allows you to do is change this security mode from standard to secured. In standard mode, the module simply acts as a non-secure OPC UA server. If you want to access any of the cybersecurity features, simply change it to secure mode, and then now you have access to all the cybersecurity features and the OPC UA security that I will cover in the next slide. All right, one of the main key features on the module is the embedded OPC UA server. I will go over the high performance characteristics on the next slide. But with the embedded OPC UA server, like I mentioned earlier, you can easily manage it using a built-in web server, not needing any additional software nor license. Also, OPC UA communications are natively secured using the standard authentication with certificates and security policies and encryption. And I will get into more detail in use case 3, where I will live demonstrate how easily you can configure this between the OPC UA server and a client. Also, NUA module allows you to have symbolic access to all your variables over the data dictionary. Now you don't have to worry about using Modbus registers. You get complete isolation between the control port, the front control port, or any network that's connected to it, and the device network that's on the backplane port and the M580 backplane, Ethernet backplane. With that, you get IP forwarding and firewall features. And part of the firewall feature is the Internet Protocol Security Tunnel, which I will demonstrate in use case 2, and ability to add firewall rules. Now you have complete control over what could go in and out of the module, go through the module. The front port, you can set IPv4 addressing or IPv6 addressing for the front 1 gig Ethernet port, which is great for high performance IT infrastructures. Security events can be logged to a syslog server with the built-in syslog capability in the NUA module. Lastly, the NUA module handles Modbus data over the Ethernet bus instead of the X bus, providing you high performance. It's transferring all the Modbus data at the speed of 100 megabytes per second over the Ethernet bus, versus, remember, on the NOC modules, they're using X bus. Now let's move on to some of the performance characteristics of the module. NUA is designed for high industrial applications, high demanding industrial applications. The built-in OPC UA server has no impact on the process control or the CPU cycle time. Each module, you can support up to 2 OPC UA clients at the same time. And you can have up to 2 modules per M580 system. And also keep in mind, NUA module can be used in standalone system or hot standby system. And if you need more than 10 clients, then you would need 2 modules. Then the M580 system could support up to 20 OPC UA clients at a time. As far as the tag database management goes, you can access up to 100,000 variables over the data dictionary from the NUA module. Dave's going to go into more detail later on when he's covering the new OPC UA client function blocks on what monitor items and subscription is, because these are part of the OPC UA server and client setup. But as far as numbers go, the server could read up to 50,000, or it can monitor up to 50,000 items. It could have up to 40 subscriptions at the same time. And in those items, it's looking for up to 20,000 value changes per second. And this is based on integer variable. As far as sampling rate goes, it gets low as 20 milliseconds. Now let's move on to the architecture use cases so you can see the true power of the NUA module. Use case 1 simply allows you to secure communications between engineering workstation and Modicon M580 via IPsec tunnel, or Internet Protocol Security. Now with the IPsec, you're also able to secure any non-secure communication protocols, such as Modbus TCP. Let's take a quick look at an example scenario here that will help you understand this use case. Typically, you have an engineering workstation with EcoStruxure Control Expert, which is the programming software for Modicon M580. But it can be any other software application that needs to access M580. In this scenario, the engineering workstation can access M580 over the network through a network router or a switch. And that's how it's able to reach the M580 system. But there is no cybersecurity enabled on the M580 currently. And since it's not enabled, now a person could easily access the network anywhere between the engineering workstation and the network and M580 system. And they could view the data between the two, right? Now, that's a huge cybersecurity issue because they can easily trace all the network packets that are being sent between the engineering workstation and the M580 system. Easiest way to prevent such a cybersecurity attack, simply add an NUA module to your architecture and enable the IP security tunnel. I will demonstrate this in the next use case and show you how easily it could be enabled. With the IP security enabled on the NUA, now the only engineering workstation defined in the NUA configuration can access M580 data. IPsec feature adds security and encryption between the 2 devices. That same person now will not be able to access nor see any data to and from M580. Let's move on to use case 2. In use case 2, you can access field devices that are part of M580 distributed I/O over the secure IPsec tunnel that we talked about in use case 1. I will demonstrate how easily we can access a VFD Altovar 630 process drive from engineering workstation that is on a different isolated network. This is easily achievable with built-in IP forwarding in the NUA module. Let's take a look at my current architecture and network setup. There are 3 isolated networks in this example architecture. There's network A, which is part of my engineering workstation. There's network B, which is part of the M580 backplane network. And then there's network C, which is part of the M580 private distributed I/O network. Embedded IP forwarding capability on the NUA module allows me to bridge over the engineering workstation to my M580 backplane and access the M580 distributed I/O network. Key thing here is to ensure network configuration is set accordingly. My engineering workstation is set to 192.169.1.200 with the subnet mask of 255.255.0.0. The subnet mask is also going to be the same pretty much on all of my networks. Gateway is set to my front control port of my NUA module, which is 192.169.1.50. The NUA module acts as a gateway for engineering workstation, M580 backplane network, and any other connected field devices. A network gateway is a connection point between two networks, allowing data to flow between them. Moving on to the NUA module configuration, the front control port is set to 192.169.1.50, same subnet mask. Backplane port is set to 192.168.11.3. Now on the M580 network configuration, the backplane port is set to 192.168.11.1, subnet mask set to 255.255.0.0, and the gateway is set to my backplane port of my NUA module, which is 192.168.11.3. Finally, the field device, which is my Altovar 630 process drive for this demonstration, set to 192.168.1.30, which is part of the private distributed I/O network for M580. And the gateway is also set to the backplane port of the NUA module. Once again, the network configuration is the key to be able to bridge over to the isolated networks with the NUA IP forwarding. And one additional step you do have to take when you're trying to do this from engineering workstation with Windows is that you have to create a persistent route, which could be easily done so using a command prompt and issuing an add route or a static route command. And this allows it to reach through the NUA and go over to your, their networks. But this could be avoided by adding a router between your engineering workstation and the NUA module if you do not want to create a static route in the Windows operating system. Let's move on to the demonstration now. So let me first show you what my network configuration is on my VM. So as you can see, my IP address on my virtual machine is set to 192.169.1.200, subnet mask of 255.255.0.0, and gateway is set to my control port of the NUA module 192.169.1.50. And keep in mind, the IPsec feature or the Internet Protocol security is disabled on the NUA module because I want to demonstrate the power it has before and after with Wireshark. So I'm going to use, to connect to the device, the VFD in the field, I'm going to use the SoulMove software, which is a free software we use to program all of the all-to-wire process drives. And real quick, I could show you the configuration I have for the connection. You can see it's set to Modbus TCP, and it's on a totally different network, 192.168.1.30. Now I'm going to simply connect to it and show you how easily I can connect. And there was no other configuration done for this, right? Just what I shared over my presentation slide. And as you can see right here on the left corner, I easily connected to the drive. Now I have the ability to program, configure, do whatever I like over the network to this drive. While this is connected, let's take a peek on how the network traffic looks like from my engineering workstation to the VFD. I'm going to open up a Wireshark, and it's my Ethernet 0 adapter that I'm using. So I'm going to start the trace, and immediately, as you can see, you could see all the Modbus TCP traffic between my engineering workstation and the drive that's out there in the field, which is on the private network. It's pretty much going to be the same for most part because I'm not doing anything else. So I'm going to stop this trace. I'm going to pick one of the packets here. So as you can see on the network, it's completely exposing the IP address of my VFD without that, since Internet Protocol security is disabled. So I can see my IP address of my drive that's on the private distributed I/O network. And I can see the IP address of my engineering workstation, which is fine, but you do not want to see the IP address of the VFD. And if you come down here, you can even view the data that's being exchanged between the two devices. If somebody wanted to manipulate your system, they can use this information and they could do something with this, and you do not want that. It's a huge cybersecurity risk. So let's go ahead and enable IP security on the NUA module. But let me disconnect from the drive real quick. So I'm going to disconnect. And then I'm going to close this. We'll come back to this to show you after. So I'm going to log into my NUA module now to configure cybersecurity. So this is the home page when you first log in. And then from here, we're going to access cybersecurity setup. Under settings, we're going to go to IPsec. And then here, as you can see, the service is currently disabled or off. I'm going to go ahead and enable it and add a new link. And this is the link that allows you to create a tunnel between the engineering workstation. So I'm going to enter my engineering workstation IP address. And keep in mind, you can have multiple links. So you can have multiple engineering workstations that could go through the same tunnel to access the M580 through a NUA module. So I'm going to add my IP address of my engineering workstation. And you want to leave the confidentiality checked because this adds encryption. And client types Windows. And there's another option for device. That's if you want to set up IPsec between two NUA modules. And PSK stands for pre-shared key, which it generates automatically once I hit submit. So that's the first step. And you saw how easy that was. The second step is if you go to this gear icon, you download this script. Essentially, it's a batch file. And what it allows you to do is it automatically creates Windows firewall configuration rules and sets the tunnel between the NUA and the engineering workstation. So real quick, before I run the script, I'm going to show you what it does. If I go to my Windows firewall settings and go to my current security rules, there's nothing here, as you can see. Now I'm going to run the script. You do have to run it as an administrator. And it's going to do its thing. Same key to close it. If I refresh this page, as you can see, it successfully created the configuration and rules for you. Keep in mind, on the NOC modules, you have to do this manually. All right, now IP security has been enabled. I just want to make sure I did apply I didn't apply this. So remember, when you do add the link, you do have to apply the changes here. Now, one link has been created. If you wanted to add another engineering workstation, you can do so. For this demonstration, we're only going to test it with one link. Now, I'm going to demonstrate I can now successfully, hopefully, can connect to the device over the secure IP security tunnel. As you can see, now, before IP security was disabled, then I set up the IP security and created that tunnel between the engineering workstation and NUA, and I was still able to successfully access my VFD that's on a private M580 distributed I/O network, isolated network. Let's take a peek at Wireshark and what that looks like now, right? Earlier we saw it traced all the Modbus TCP messages, so we're going to try to do the same while my device is connected, right? So let's see if it still shows us Modbus TCP messages or anything else. Wow, look at that now. So I'm going to let it run for a little bit, but as you can see, there's not a single Modbus TCP packet here now. I'm going to stop it. And as you can see, from top to bottom right now, the only two IP addresses that you are seeing is my engineering workstation 192.168.1.200 and the front control port, my NUA module 192.169.1.50, and that's it. It's not even, it's not going to show you anything. If you click on it and it come down here, you may wonder what ESP is. It stands for Encapsulating Security Payload. Essentially what this means is the data it's part of IPsec, or Internet Protocol Security, and essentially what it means is now your data has been authenticated and encrypted. And you can see how powerful Internet Protocol Security is. So I highly recommend, if you haven't enabled this yet, take advantage of it, enable it, secure your communication from M580 to your engineering workstations. Now let's move on to use case 3, which allows you to basically secure. Let's say you don't want to take advantage of Internet Protocol Security. You simply want to take advantage of the built-in cybersecurity in OPC UA. So the NUA is a server. You can secure communication from the NUA server to any clients. The clients could be, Aviva Plant SCADA, Aviva Plant System Platform, Machine SCADA Expert, or any third-party application with the OPC UA client capability. And I will demonstrate that, how easily you can configure it on the NUA and how easy you can connect from the client to it. So let's get into the live demo 2 here. I'm going to close this. We're going to go back to, let's say we're back to the home page. And from the home page, you're going to go to cybersecurity setup again. And then we're going to go to OPC UA. This is where you can configure the security settings. First thing we're going to do is configure the security mode, which is going to require signing and encryption. So, and the security policy, I'm going to leave it to basic 256, SHA 256. For a user identification token, I'm going to leave username. And submit. Second step is adding, now security settings have been configured. Now we have to follow up with authentication. Two steps of authentication, right? First is downloading the server certificate, which you can access from cybersecurity, certificate management, PKI configuration. Under device certificate, this is where you can download the certificate for the OPC NUA server. As you can see, if you're wondering when does this expires in 2049. But I believe there's a way to change this also. So I'm going to download this somewhere and easily move it to where I can find it. So I'm going to copy it over to my desktop under a folder I already created. And then I will be using, for today's demonstration for OPC UA Client, I'll be using UA Expert. It's a free software you can use to troubleshoot, OPC UA server or to simply test it, right? So first thing I'm going to do is go to Setting and go to Manage Certificate. I'm going to add the server certificate to the trust list for my client, because you have to do that on both sides, on the client and you have to do it on the server. This is the first part of authentication. So I'm going to open certificate location. And I'm going to go back to where my server certificate was saved. And then I'm going to copy it over here. And now this should add the server certificate to my trust list. I'm simply going to refresh. As you can see, it trusted the server certificate. And the second step is now trusting the client certificate on the server. So this is the client certificate I could see. And by the way, these steps may vary on individual OPC client application, but the concept is pretty much the same on all. So I'm going to copy the client certificate to my desktop here. And then I'm going to go back to my OPC UA server settings. And then for that, you go to Trust List Management, Add, and it's going to give you an option to browse to your computer. And it already browsed to my folder. And then I'm going to add the certificate here, submit, and add it, and apply the changes. Now the UA server will only allow this OPC UA client to be able to connect because it trusted the certificate. So there's a trust between both sides, right? Client and server. Last part or last step is we're adding a user and a password for the client to use to be able to log into the UA server. And this is important because this adds a second layer of authentication. For username, I'm going to simply create SCADA, and for password, I'm going to give it a random password here. Password doesn't have to match criteria, which you can access from this information icon. And for roles, keep in mind, only 2 roles allow access to the OPC UA server, which is operator and engineer. So I'm going, for this demonstration, I'm simply going to select operator. Apply. And that's it. We are done on the OPC UA server side. I'm going to leave this diagnostic screen here because we're going to come back to get the endpoint URL for the client. Now we're going to try using the security configuration, connecting to the server from the OPC UA client. So I'm going to go to this project area and then add a server. Custom discovery, and this is where I need to access that endpoint URL, which once again you can access from the diagnostic tab. It has all the information you need as far as the endpoint URL goes. So I'm going to here and add. It already added the first half, and then the rest is just the IP address and the port. So it's basically my front port of the NUA, 1.50.48.40. And now if I browse down to it, if it's successful communication that, hey, it's detected the server based on this address and you have a, communication over the network, then it will show you the name of the module. And then if I dig down further, it'll actually even show me, hey, it's bigger for cybersecurity and this is the policy and the mode it's set for the security mode. And the another step you have to take is select A, and then I'm going to add username and password that I can use to log in to be able to access the server. So it was SCADA and the password I created. Now I add it to my server list, and let's go ahead and try connecting to it, see if we get a successful connection. And bam, as you can see, it was able to browse to the server, and since they accepted my security configuration, the certificates were already added. Now I was able to browse, and now I can access the project, right? EPEC project, essentially it's browsing now the namespace within M580. Now I have access to all my variables from M580. So I can pick one variable and add it to my monitor list. It's giving me status of good, that I have good communication, and I'm reading the value of 2 as far as the data goes.
Looks like we're having some technical difficulties on Bobby's end. Bobby, if you can give us a thumbs up if you are feeling like your connection is better. If not, we can take it on from here.
I think it's running just fine, Sheena. I haven't had any problems with my display.
Are we good then?
We're good.
Okay, sounds good. So yeah, this shows you, how I successfully access the tag within M580 system or the data dictionary from the server, and you can see the value of 2. And you may wonder, hey, what happens if I change? Let me disconnect this real quick. And then let's say if you try changing the, let's say I'm not going to use this username. I'm just going to try to access the server as anonymous, right? Know your username and password. Okay, and let's try connecting to it. Immediately I get an error, bad identity token. So it's very important, right, that you have the username and password, but as you can see how powerful that is, right? So without the certificate or the username and password, you cannot access the server. All right, that's all on my end. I'm going to hand it over to Dave now. Thank you guys for your time.
Okay, thank you very much, Bobby. I'm going to share my screen, and then we are going to jump into architecture use case number 4 and look at another example. All right, so now we're going to look at architecture use case number 4, which is secure PLC to PLC communications. The BME NUA can be used for PLC to PLC communications utilizing our standard explicit data exchange function blocks with Modbus TCP. This can be done using located or unlocated variables. We could do this without cybersecurity, but a cyber criminal could view or worse, modify this data stream. With the BME NUA card, we can enable an IPsec tunnel between PLCs, allowing for secure and encrypted PLC to PLC communications. Now, our cyber criminal will not be able to intercept our communications. And in terms of setup of this is very similar to what Bobby showed you in use case 2, except rather than picking Windows as the client for the IPsec tunnel, you'd pick the device option that he showed. So now we will also look at architecture use case 5, which is standardized PLC to PLC communications. OPC UA can be used as a standardized protocol for PLC to PLC communications, as it is an open protocol that is common to many vendors. This could be used for M580s, Modicon machine PLCs such as the M262, third-party PLCs, or smart equipment. This is especially powerful because most HMI, SCADA, and historian packages are already using OPC as their communication standard. In the M580, OPC UA client connections are performed using the OPC UA client function blocks, which were introduced in Control Expert version 15.2. Currently, the M580 client function blocks are recommended for communications to third-party PLCs. For M580 to Modicon communications, we still recommend the data exchange blocks. In the current releases, the OPC UA client function blocks do not support OPC UA security. Security, as well as other enhancements, will come in future releases. For our live demo, I will show OPC UA connectivity between two Modicon M580 PLCs. Before jumping into the demo, I will give you an overview of the controller requirements and programming sequence for OPC UA communications. There are some minimum requirements for the OPC UA client function blocks. EcoStruxure Control Expert must be version 15.2 or higher, and the Modicon M580 CPU firmware must be version 4 or higher. The OPC UA client function blocks can either be initiated from the M580 Ethernet ports, as in the diagram here, or through a BME NUA card. If the BME NUA is used, it must be firmware version 2.0 or higher, and the rotary switch must be set on standard mode or on secure mode with the OPC UA security mode set to none. That's because, as I mentioned, there's no security in the current release of this. There are also Control Expert project settings required for the UA client function blocks. If the BME NUA module is being used and we want to use it as an OPC UA server, we need to enable the data dictionary. The OPC UA server uses this to access variables. It is also a good idea to enable the preloading of build changes, as this prevents the loss of communications while a project is being downloaded to the CPU. As another option, only HMI variables can be enabled so that we can refine the list of variables that the OPC UA server can access to only those that are selected by the user. For the client function blocks, we must always enable directly represented array variables and allow dynamic arrays, as these features are utilized by the OPC UA client function blocks. The OPC UA client blocks require a specific sequence of coding to operate. There's a slightly different programming sequence for reads and writes, which are our explicit data exchanges, versus subscriptions, which are pulled data exchanges. First, we will look at explicit reads and writes. So the programming sequence is to prepare the connection, then perform as many explicit data exchanges as needed, and then clean up the connection. So first we'll look at the prepare phase, which we only need to perform once. When preparing the connection, the UA connect block is used to create a connection, also called a session, with the OPC UA server. The UA node get handle list instruction is then used to translate node IDs, which are the addresses of OPC UA items, to node handles, which are a simple D word, to optimize the OPC UA request payload. All subsequent requests are now handled through the easier-to-manage node handles rather than node IDs. Now that the connection is prepared, we can perform multiple read and write exchanges as needed. The UA read list instruction is used to read the values of multiple nodes, and the UA write list instruction is used to write values to multiple nodes. The OPC UA client connections and handles take up memory in the OPC UA server, and the handles will be invalid if there is a disconnection. Therefore, it is required to clean up our connections if either the OPC client or server must be taken offline, or if the connection is lost. To clean up connections, we use the UA node release handle list block to release the node handles, and we use the UA disconnect block to close the connection with the OPC UA server. Now, what happens if we don't clean up the connection? For most servers, once the connection times out, they will automatically clean this stuff up, but it's still a good idea to make sure that we are coding all of this properly in case we're using a server that does not have a perfect implementation of the UA specification. So now we're going to look at the sequence for monitoring items by subscription. So what is an OPC UA subscription? It's a method of pulling a list of items at a specific update rate. Now, unlike some other methods of pulling, OPC UA subscriptions use a callback method so that the OPC UA client only receives updated data when a variable value has changed. The programming for a sequence for a subscription is to first prepare the connection, then we subscribe to items, and then we clean up the connection as necessary. The prepare phase for subscriptions is very similar to the prepare phase for explicit reads and writes. The difference is that after we connect to the server and get the node handles, we must also create a subscription. The UA subscription create creates a subscription that can pull monitors items, and it will update the client at the specified publishing interval, which is basically your pull rate. Now we'll look at the execution phase for a subscription. First, we need to add monitored items to the subscription with the UA monitored item add list. So previously we created the subscription, which is our polling group. Now we're going to add the individual variables we want to pull to that subscription. When we perform this instruction, we also need to choose either a controller sync or firmware sync for our subscription. So for controller sync, we call the UA monitored item operate list instruction to transfer variables from the subscription to the PLC. So this would require the programmer to initiate an instruction to update our pulled values. If we choose firmware sync, which is preferred, the monitored items will automatically update their values at the specified publishing interval. In firmware sync mode, we can optionally call the UA subscription processed instruction to check if values have actually been updated. When we are ready to move into the cleanup phase, we can first call the UA monitored item remove list to remove the monitored items from the OPC UA server. Now we'll look at the cleanup phase for a subscription. This is very similar to the cleanup phase for explicit reads and writes. The only difference is that before we release the node handles and disconnect, we first must delete the subscription. The UA subscription delete instruction is the instruction that does this. Now we can call the UA node release handle list and the UA disconnect blocks to finish the cleanup. Before jumping into the demo, I just wanted to recap the architecture that's being used. The M580 on the left with the BME NUA card at 172.16.0.2 will be using the OPC UA client instructions to connect to the BME NUA OPC UA server at 172.16.0.3. So now I'm going to bring up the VM where I have a couple instances of Control Expert running. Now, before jumping into the demo, I just wanted to discuss a couple things here. So for everything I'm doing here, you're going to see me doing a lot of manual mouse clicks. That's just for demonstration purposes. Any of the coding here can be sequenced and automated just like usual with explicit communication blocks. And we'll also see a lot of code around these blocks. So here you'll see the UA connect block, and around it you see a bunch of resets and moves and stuff like that. All of this code here you'll see on every instruction, and I'm using it to just buffer my statuses and my error codes. I'm doing that because the execute pin, when it's high, will execute any of the UA instructions, and once it's completed, the error IDs or the error message will have a value in it. But once execute goes back to a 0, these values go back to a 0, and I lose that status information. So for troubleshooting purposes, it's a good idea to buffer this. So Going forward, you'll see this code, but I'm just going to discuss the main block here. Another piece that you'll see on every block is that they have a timeout. This is a local timeout for this block. So if I try to connect to the server and it doesn't work within 5 seconds, that means that this block will time out. The controller will then give me an error and an error code associated with this. So this is the code in the client controller. And then I have a second instance of Control Expert running, which is connecting to the server controller. So there's 5 tag values here that we're going to write to when we get to the write instruction. We can see right now in this animation table that all their values are 0. So we'll be back to this program when it's time to do some writes. All right, so now let's look at that first phase, that preparation stage. And we're going to do some preparation for a read, a write, and a subscription. So if you recall, the first thing we have to do is connect to the server. Now, the first piece of connecting to the server is having the address of the server, which in the case of OPC UA, the address of a server is a URL. Now, in my case, I'm using an N580 PLC. So just like in Bobby's demo, I can log into the web page of the card and go to the diagnostic screen where we will see the endpoint URL. So that's what we've entered into the client instruction. We also have some session connect info. So if I go into my variable for the session connect info, you'll see I've loaded values for a session name. This is just a string that's shared between client and server to say the name. We have a transport profile, which just always has to get set to a 1. And then we have a session timeout. This is just telling the server and the client, hey, we need to, if we lose connection for more than 30 seconds, clean this session out of your memory. And then we also have a monitor connection here. The PLC will basically just do a keep alive every 10 seconds in case you're not actually doing anything, like you're not really reading or writing data or subscribing to anything. You'll notice a lot more variables we could put in here as part of the data structure, but these will come in later releases to be used with security. So now that we've set this up, I'll go ahead and execute this block and we should get connected to that server. You can see here that my error handling code reported we have an active connection. And you'll notice we also got out of this a connection handle, which is just an integer value that we use to symbolize this particular server client connection. And we use that connection handle in all of the subsequent blocks. Now from here, we'll move into preparation for an OPC UA read. The first step here is to get our node handles. So into this block, we'll load the connection handles so we know which client-server connection we're using. We'll say how many nodes we're reading, and then we'll give it the node IDs. So what do node IDs look like? So if you look at node IDs in a UA server, they have 3 pieces to them. They have a namespace index. UA servers can have multiple namespaces, so this is just a number to indicate which one you're using. We have an identifier type. This could be a string, which is a variable name, or it could be numeric, which means that server just classifies everything as a integer value. In this case, we're using 1 for string, and our identifier is just the 0 colon the variable name in the other controller. Now, this here of namespace index 2, identifier type of string, and the identifier being 0 colon variable name is always true if the M580 UA card is the server, but if something else is the server, it might not follow that exact syntax. So what you could do is open up a tool that has UA browsing, like this UA expert tool that Bobby already showed you. Pick a variable, and then in your attributes, one of the first things you'll see is the node ID. So you can see here it's exactly like I was talking about. Namespace 2, identifier type string, and then an identifier that happens to be 0 colon the variable name. Here you can see the variable name, and here you can see the identifier. So that's what we've put in for all of the node IDs in this program, all 5 of those that we're using. So now we'll go ahead and we'll get those node IDs here. By executing this, we'll see that we got back a success. So now our node handles array is full of the integer value that symbolizes each of those variables. Now we're going to go ahead and do the same thing for some variables we're going to write to. And we're also going to do the same thing for some variables we're going to subscribe to. So we could see all those node handles came in correctly. Now, what we have to do on this prepare phase here is one more thing for our subscription. So for our subscription, we also have to create a subscription. Just like everywhere else, we're going to get a handle out of this. So we'll get an integer value that's going to symbolize this subscription for us. And we'll feed in the connection handle. And we'll also have a variable here called publishing enable. Publishing enable just says, hey, I actually want you to give me those data change event updates for this. So we'll set that to a 1, so we really get data changes. We have a priority value here, so we can prioritize this subscription if we had multiple subscriptions. In this case, we only have 1, so I'm leaving it to 0. And then we also have the publishing interval. I've set it to 2 seconds. This is just the polling rate for this subscription. So I'm going to go ahead and execute this. It was successful, so now we've created a subscription. So then from here, we've prepared the connection. We just have to do that once. We connect to the server, we get those handles. If we're subscribing to data, we create that subscription. So now all we have to do is do our actual reads, writes, and subscriptions. So before we do that, if we want, we have a get status block that we can use to check if our connection is good. So I'll go ahead and execute this here. As you can see, it executed. It still tells me I have an active connection, so we're still good. So now I'll move on to doing an actual read. So to do an actual read of data here, what we're doing is feeding in all of those handles we got earlier. So we connected, we'll tell it which connection we're using, we'll tell it how many nodes we're reading, we'll give it those values symbolizing our nodes, our node handles. And then if we were reading metadata instead of data, we could fill in this node additional infos, but we're just reading variable values here, so we don't have to do anything to that. And then the last piece you're going to see is something that's going to be a little bit unique to the UA instructions. It's the variables data and structure. And we'll use this for writes and subscriptions as well. So I'm just going to show this to you on the read. But when we go into the variables data structure, we've got two things. We've got a node data type. If you look in the help file for the instruction, it'll give you this table that'll say, hey, give it a 1 for a bool, give it 3 for a byte, 7 for a udint. Whatever you have, you put that in there. And then we also have this PBY buffer, which I needed to show you from the other screen here. So let me pull this back up. The variables there. There we go. So this is a reference variable. So what it does is it basically acts as a pointer to point to a variable in our actual program. In this case, the UA read bool var is the name of the variable that it's going to put that value into. So we're using a pointer to move data from this block into a variable in the instruction. And then another thing you'll notice here on what we're getting out that's a little bit different is we're going to get out some timestamps. So we have an array of timestamps for all the data. UA natively comes with a timestamp on the client end. So any value that we read through this instruction or from a subscription will get an updated timestamp. So now I'm going to go over to my animation table and we'll look at performing one of these instructions. So we should see these read values change. So I'm going to go ahead and execute this now. So see I got an update to all of those variables. And you'll also notice that they're not changing. So if I execute this again, it'll initiate another read and read it again. So these reads and writes are explicit instructions. We have to execute them every time we want a data change. And then you'll also notice I can open up that timestamps array and I can tie a timestamp to this data. So it'll show it in a date time format and also the number of milliseconds here in another variable. So if I execute this again, you'll see that timestamp change. So that's when that data came in. So now that we've done that, we've looked at a read, we'll go ahead and look at a write. There's not much to talk about with how you set it up because it's the same thing as a read. The only thing we're missing is the timestamps. And this is because we don't have to load the timestamps in. We're going to write it to the server and the server is just going to timestamp it when that comes in. We don't have to do that ourselves. So if I execute this, we'll see on the other PLC beforehand, we've got all zeros in those variable values. So if I come back to this program here, I can put a value in all of my variables. So go ahead and put something in here. We'll send the classic hello world here in our string variable. And now we'll go ahead and send this. Said it was successful. If we look at the other PLC, we'll see that we got an update. All those values are the same. And just like the reads, this is something that happens one time. I'd have to execute this again to send the data. Now we'll look at a subscription. So this is where we're pulling data, and there's a little bit more to fill in here. So with pulling, with the subscription, we have that subscription handle that we got when we created the subscription. We have the number of nodes that we want to read from. We've got our node handles, and then we also have the sync mode here. So the sync mode, this is where we were talking about earlier. There's controller sync, where the engineer manually has to ask for the subscribed data. And then there's firmware sync, which is a value of 2. That's what we're using here. So with firmware sync mode, as soon as I execute this, I will get updates to the variables automatically. Then we have the node additional infos. Just like before, I would only really need this for metadata. Here I'm reading just values, so I'm not worried about that. We have a variables array. That's the same as it was for the reads and writes. And then we've got a little bit more data here. So we have some monitoring parameters. I'm not going to go into this, but these are additional things you can add. So instead of just saying update me when data changed, maybe you want to add a deadband as well. And then we also have some status variables. We have values change. So this is just a Boolean that says, hey, did this variable actually update, or did no value change from the server? And then we also have a min lost value count. This would be, hey, I'm reading variables at a faster rate than I'm getting them back from the controller. Trigger an error for me and tell me how many values I've lost. So once we've added all that stuff in, we can execute this, and we'll see that once we do this I'm reading an integer array. So once I subscribe here, we'll start seeing these values update at the 2-second update rate that we put in when I created the subscription. So see here, every 2 seconds, these values will change as long as they've changed in the server. And so unlike reads and writes, this is not an explicit exchange. So once I put this in here, it just keeps happening until we stop it. So it's great for, a continuous connection of reading data. Since we're in that firmware sync mode, we can, if we want, just check to make sure it's working. We have this UA subscription processed here. I can execute this, and it'll tell me if we're getting published. I got a 1 on my published bit, so we know we're good. It's actually publishing data for me, and I don't have any errors. So from here, all we have to do is just keep doing reads and writes and looking at our subscribed data as long as we need. If something happens, like I know I'm going to shut this PLC down for maintenance, I would want to clean up the connection. So if I want to on the subscription, I can remove my list of items. And if I do this, you'll see my data here stopped updating every 2 seconds. Now from here, I can go over to the cleanup and remove all my node handles and my subscription from the server. Now, before I do that, I'm going to bring up the web page here. What you'll see I have 2 connected sessions. So that's 2 clients. One of them is UA Expert and one of them is my client PLC. So as soon as I'm done cleaning up, we should see this go back to 1. So we'll come back to this page after we do the cleanup. So the first stage is just take all those node handles we created and get those out of the server. It doesn't need to keep track of those nodes that we're reading anymore. So I'll go ahead and clean those out. Now on the subscription side, before I do that, I have to delete the subscription. That's just because the subscription uses the handles in it, so we want to remove that first. So first I'll delete the subscription. That happened successfully. Then I'll remove those node handles. So once we've done that, let's see, all those were successful. So we've cleared out all the variables and the subscriptions we're using. The last piece here is just to disconnect from the server. And once I do this, I'll set this to 1. We'll disconnect. Then you'll see here, as soon as this website updates here, there you go. Now we're down to 1 connected session. So that's really the sequence here for the UA client instructions. So at this point, we're done with the demonstration that we had today. So what I'm going to do is I'm going to go back to show just a couple summary slides, and then we will open it up for questions. So a quick summary of the BME NUA 0100. We can use this card for as a high-performance OPC UA server. However, it's not just a simple UA server module, but a very advanced communication module that can act as a firewall between the M580 and any network that is connected to the front port. It provides complete isolation between the backplane port and front control port without jeopardizing transparency. This is via the built-in IP forwarding. We can simply manage the OPC UA server and its cybersecurity functionalities via the embedded web server. This eliminates the need for any additional software or licensing. And the BME NUA also increases performance when used for Modbus TCP data, as it uses the Ethernet backplane instead of the XBus. And with the presentation today, we're also providing a list of some technical assets. So we have some YouTube videos and some e-learning stuff that you can go to view videos of how to set up a lot of things with the module, including some of the things we went over today. And likewise, we have some TVDAs and knowledge base articles that can help us to see how to configure these as well. So these links can take you to these additional resources. So at this point, I'm going to stop sharing my screen and we'll go through and try to answer any questions that we have.
Awesome, David. Thank you very much. Before I go through some of the questions, let me just point everyone to the chat where I put a short survey in there. Simple question: how do we do today? Your time versus the information that you got, the learning that you received today. And then if there's anything else that you would like us to present to, please take a look at the chat, and it really helps us. It helps us get better. Feedback is always good. So let me ask a couple of questions here. Can I configure / program my M580 PLC with Control Expert via a workstation on my network connected to the control port of an installed NUA module? Or is the NUA designed for OPC UA traffic only? So how do I secure this configuration program traffic?
It's not restricted to OPC UA server only. The from control port can be used to, for Modbus TCP, and you could use the Control Expert software to access M580 and program it. And how you secure it is by just enabling IPsec feature. That's pretty much what that use case earlier was.
Excellent. Okay, so in a hot standby system, how do you configure both NUAs for IPsec? If you change the setup in one, does it automatically configure the standby unit? Anybody have the answer?
So I believe those have to be configured manually, but I'm looking into it right now. We'll get back to that shortly. I'm not 100%, unless Dave knows.
Okay, so we'll get back. The question is that we'll get back to you on that. And this, I guess, this one's directed to you, David. So the DFBs can perform data exchange to a PC running an OPC UA server potentially. Actually, I'm not really sure.
Yeah, absolutely. I mean, in my example, I'm showing the communication between two M580 PLCs. That's because we were kind of showing it as a PLC to PLC use case, but you could absolutely use this to read from a PC-based UA server, a Linux-based OPC UA server, or even some HMIs, like our operator terminal expert HMIs can be OPC servers. So there's a lot of potential options that you could be reading or writing to with those blocks. Really any server without security, because there's no security in the current release. That's something that will be added in the future. So eventually we'll have that capability as well.
Okay, thank you. I have another one here. I think it relates to the PLC to PLC. If we have to take the PLC down, We have to follow the sequence to close the connection. But what if the PLC crashes? It would be normal to reset all the connection after we restore the PLC.
So if the PLC crashes, the thing to keep in mind is that if the server in use is a properly set up UA server, what'll happen is when we set up that in the initial connection, if you recall, I put in a timeout of 30 seconds for my UA connection. So what should happen is after 30 seconds, the UA server will just clear out all that information. So if I had just turned off my client PLC in my lab here, the server PLC on our end, the other UA card would just clear out all that data after 30 seconds. So it wouldn't be a showstopper. But, sometimes there might be a bug or someone's server might not work correctly and it might not do it the right way like our UA card does. So it's still good practice to put all the cleanup stuff in, even though technically it should work without it.
Okay. Then I think I have a last question here. I guess I'm not sure exactly what this question is, but maybe you'll know, David. So what if any resources are needed by a remote located party, such as a control system integrator that is trying to support his clients whose architecture includes the NUA module? Does the integrator just need the creds established as a client, some hardware or other? So I guess he's trying to talk about if a system integrator is, I guess, remotely trying to connect, to a customer PLC, for example. I'm not sure. Do we know that answer?
Yeah, I guess that would depend how you're trying to connect and whether or not security is enabled. We didn't go into all the firewall configuration stuff, but you can choose, you can choose what IP addresses and such are allowed through the module. So if the goal here was to allow, a system integrator through, but not everybody, you would put those rules into there. And then, if you wanted that system integrator to use the IPsec on the module, then they'd have to be terminating that tunnel somewhere, like on one of their computers. But with the use of those firewall features, you could kind of pick to let that integrator through. Or if you don't want security at all, you would just have that turned off.
So the integrator could be a part of the secure communications. You just have to set it up that way.
Right.
And Lou, this is Robert. That is correct. We've done that where the integrator would have to have credentials assigned to the M580 in order to make the secure connection. In an unsecure connection, all they would need is the OPC UA IP address and the port number to get into it for programming with EcoStruxure Control Expert. Once you make the connection, of course, if the client has established any passwords, application passwords, then you would need those to get in.
Okay, so we are at the end. Thank you, Robert. We are at the end of our time allotment here. It's 2:31. Actually, we're a minute over. There are questions still keep coming in. I will remind you that of the survey that's in there, there also is a link or one of the questions is, do you want more help? And if you can put your contact name and number in there, and we will have someone give you a call to talk about your specific application. It's anonymous, so I need you to put your name. The survey itself is anonymous, so I need you to put your name and number if you would require some additional civil help, hand-holding, or information regarding the NUA. So that is in the chat. Again, thank you very much for joining today, and we're going to be looking to have another one in October. And again, thank you very much. This concludes our video today, and I want to thank all our presenters here, both Robert, Bobby, and David. Thanks, everyone. Talk to you soon. Bye-bye.